Off to a good start. Already broke it. So apparently this is going to be the second best talk, because Adam's already given the best talk of the session. So I just want to give an overview of Havok Physics within the DOTS framework. And I'm really going to touch just briefly on the Havok and Unity partnership. There's a ragdoll demo going on over there. A look at Unity physics and the sort of systems in place there. Adam's already touched on some of them if you've already seen his talk. And then I really want to emphasize the differences between Unity and Havok before sort of touching on some of the potential roadmap ideas that we have going forward. So at GDC, we announced a partnership to put the Havok technology inside Unity. If you don't know Havok, we've been powering AAA game titles since the last millennium, in fact, on many different platforms. You want to replace it now?
Yeah.
Okay. Testing. Okay. Take two. Should I start at the beginning? So here are some of the titles that we're powering at the moment. Maybe not just physics, but also some of the other technology pieces that Havok have. And we're all on the platforms that everyone's going to be interested in. Just as a bit of an anecdote, I walked into the local supermarket shelves, and I sort of thought I'd put a Havok logo beside all the titles that we're in. Bit of double counting, but we'll ignore that. And that's just sort of a representative show of the sort of titles that are being powered by Havok at the moment. But we really want to work together with Unity to put the Havok technology out to as many people as possible. So let's see how that's going to actually work. So if we're looking at Unity physics, Adam gave a very good overview of that particular side of things. But I am going to touch and repeat a few things that he said as well, just to highlight specific areas that need to be touched on so that we can see what the differences are between the two core simulations. And arguably, whenever I'm talking about these systems at the start, we're really talking about maybe a DOTS physics rather than a Unity physics, because the idea is that we want to have a data-orientated approach so that, as Adam said, we can have a back end that's maybe focused on simulation for robotics or a simulation for fast performance in a game environment. So the very big overall picture for ECS is the number of the conversion pipeline from the game object world to create the entity data that we covered in the last talk with the physics components like the physics collider and the physics velocity. And then there's the build physics system that is taking that data, converting it into a slightly different format that's optimized for runtime and a large number of random access queries. And then there's the step physics, and this is the piece that we're really going to talk about in this talk, because it's the one piece that can be swapped out. We're using the same data from the authoring side through to the I-component data. All of that's going to be fed into Unity physics or Havok physics, so we want to touch a little bit more on what's going on there. And then once that system has done its work, the final export physics system takes that optimized for runtime data and puts it back into your component ECS data. So what sort of data is going into the step physics world? There's only really two sets of information. The collision information, which was the colliders that Adam showed how you can convert from your scene data, and the transform, the position in space and the rotation. But there's also the dynamic information at a particular point in time, which would be the velocity, the center of mass, the orientation of that body in motion space. And whenever the step physics world does its thing, you're going to get out a second set of this dynamics information at a second time. The fact that we've got a collision world and a dynamics world, a dynamics physics world, means that you can be doing queries on that old T0 information at the same time as the physics is performing its simulation to move all that data to T1. The other set of information that you're getting out of the simulation backend is a set of contacts and triggers. So contacts, obviously, I have collided with this bit of the floor, and you might use that to spark off sound, or you might use it to spark off some particle effects like sparks. And also triggers. You've got an overlapping object. I've entered a particular area. I've got a particular area that's represented for an explosive force, and that would be part of the trigger event information. So let's dig in a little bit into the step physics world. So there's three main stages that we want to look at. How familiar is everyone with sort of rigid body collision detection and response? A few hands up. Excellent. So I might be repeating myself a little bit, but it's worth highlighting some of these pieces. So we'll talk about the broad phase, the narrow phase, and the solve step. So both, if we take the data to one side, it's going to be a common data that's entering into the step physics world. Unity physics and Havok physics are both a speculative continuous collision detection set of implementations. So that means that at the first step, when we're dealing with the broad phase overlaps, we're expanding the ABB of a dynamic body by the velocity that that body is moving at. And we're using both the linear and the angular velocity to make that expanded shape. So that rather than just having the dynamic, so any time I show an image here, the you'll see a sort of checkerboard type gray color for static bodies and a orange color for dynamic bodies, orange-yellow color. So in this particular case, because the ball is moving down to the right and we've expanded the ABB, we're getting overlaps onto the static pieces. So the first stage is to find all of those dynamic overlaps and also the dynamic static overlaps. And we want to get those arrays separately. And once that piece is done, you're getting a callback that you can go, I now want to look at this data and manipulate it if you want. So there is a simulation callback at this stage where you can, it's called post-create dispatch pairs. And you might want to use this in a game use case, for example, where you want to turn off collision detection between a bunch of bodies that you've spawned in the world and they're all overlapping each other, but they're going to explode anyway. So you don't want those pieces colliding with each other, and you know they're going to be exploding out. So I might as well remove all of the overlapping pairs for that particular use case. Now, you could do that with a collision filter, but you don't really want to have to mess about with that sort of authoring data in a runtime environment. So that's a good use case for that particular callback at the broad phase overlap level. The next point, when you're dealing with the narrow phase, you're creating all of those contact points. You're getting the normal, you're getting the closest distance to the objects that you've overlapped with in the previous section. But you've also got another callback, post-create contacts. And what you might want to do with this is either maybe backface culling on a mesh object so that you can only collide in one particular direction based on face winding. Or it might be like a displacement map type idea. So even though I might have a flat tessellated plane for my level, I could have a callback at this point so that I add a little bit of a jitter to the contact normals as the body moves across, and adds a little bit of detail. So the last point then is the solve, where we're building our contact Jacobians. Please don't ask me what a Jacobian is or how to describe it. It's a magic box. But we're creating two types of Jacobians. Friction ones for the contacts, so the body sliding across the floor or stacking on top of each other. And then the trigger Jacobians for just an overlap of so a body entering a particular volume. And at this particular point, there's another callback that you can hook in to the system. So it's very important to note that we're trying to make sure that this is not a black box, that you can see the data clearly going in, and see the data clearly going out, and you can process and manipulate that data as it goes through the pipeline. So in this particular case, the create contacts Jacobian is useful if you're wanting to do something like fake mass inertia. So you might have a physical body in the scene. You might want to have like debris bodies that are quite light but still dynamic and would effectively move, say, a character off from its position. But at this point, we could hijack the contact Jacobian, and pretend for that moment that the character's got an infinite mass. So you can do a lot of interesting things with that. Another idea is like a soft contact. I could allow the collision response to be slightly less than it would be if I just left it to its own devices. Another example might be a conveyor belt. You don't actually want to have a moving conveyor belt in a scene if you can get away with it. So if you just have a static box, but you can fake a surface velocity, and this at this point in the flow of the simulation, where you could grab the contact points or the contact Jacobians with that conveyor belt object and pretend that there is an actual surface velocity and have it move along. And finally, we're actually solving all of those Jacobians. And it's worth highlighting that we solve the static contacts last. So we can make the dynamic overlaps and contacts get processed and solved, and then the static overlaps with the dynamic objects get solved. Now, I just want to highlight one title that's already out in the world. It's on Steam. You can go and grab it right now, and they're building a sandbox where you can put your own systems together. And it's quite amazing how many sort of physics toys that the community's already created. And this is downloadable now. It's using Unity Physics. And the Reddit thread is actually quite amusing to see all the sort of different experiments people are doing. So inside the Unity Physics package, it's providing all of those callbacks. It's dealing with all that information. Hopefully you can see that you could replace that with your own if you wanted. You could expose the same sort of callbacks and allow other people to manipulate your simulation. But in the Unity Physics package that you download today, we've got the build physics world and the step physics world. But ultimately what the step physics world is doing is it's providing an eye simulation interface, and it's providing 3 implementations. One is just a dummy simulation so that you could have no integration going on. You would just have your collision world and do static queries, but you could set up a step physics world to be simulating nothing, doing nothing with the simulation. There is a simulation implementation, which is the Unity Physics, and there's also inside the Unity Physics package, there is an implementation called Havok Simulation. Now, it doesn't do anything whenever you just have the Unity Physics package on its own, but it's there so that you can sort of hot swap in the UI for the moment. So if we start looking at Havok Physics then, and some of the differences between Unity Physics and Havok Physics. Havok Physics has been released. I think it was released yesterday. It's available in the package manager for download. Make sure you show preview packages in order to see it listed in the scene. And it has a dependency on the very latest Unity Physics at the moment as well. In order to turn on Havok Physics, if you've got any demos, you can actually get the Unity Physics demos from GitHub. And in order to turn all of those demos over to using Havok Physics, there is one prefab with all the physics settings in it, and it's just a matter of changing from Unity Physics over to Havok Physics. The same authoring data is used for the conversion, the same component data is used for the runtime, and at this particular point, we're just swapping out the back end. Now, that's not to say there's not going to be some differences between Unity and Havok, so let's look at those. They fall under 2 main categories, performance and behavior. And let's look at sort of the individual pieces in each of those two main areas. The first one is in penetration recovery. Now, I could repeat this every slide, and Adam's already said it, but the core difference going on here is the fact that Unity Physics is stateless. We're trying to be able to say all the data is there. You can just replace it with a previous frame and have the simulation continue. Havok Physics has got a cache, and it is a stateful physics engine, so it's getting a lot of benefit from that. And arguably, all of these differences come back to this has got state, this has got state. So rather than putting it on every slide, state versus cached, or stateless versus cached, I'm just going to say it now, and hopefully you won't have to get an earful of it every frame. So what is penetration recovery? In this particular example, we've got, again, the tessellated, or the checkerboard are static objects, and the orange or the yellowy Havok type color are dynamic bodies. So what we've got here is various levels of penetration between the dynamic bodies within static bodies and within other dynamic bodies. Now, because Unity Physics has no state, has no cache, we have to be a little bit more aggressive. The solver's a little bit harder in dealing with interpenetrations with static bodies. And again, we also already mentioned that we solve those static contacts at the end, just to make sure that they're not violated. So that means that whenever we do actually run the simulation here from this starting ground, the more something is interpenetrating with the static body, the more aggressive that push out from the static body is. But you also see it's a much smoother flow out of an interpenetrating state between two dynamic bodies. So you have no option but getting that particular behavior, but if you do move to Havok physics, the nature of the cache means that we can control that penetration recovery. If you want the explosive force, you certainly opt that in and add that force yourself based on the penetration depth, but at least you've got an option now. So that's one difference. And just here are them, the two together, just for visual highlighting. So what you're also seeing here is the debug display that Adam mentioned in the previous talk. So the green boxes that you're seeing, the contact points that you're seeing, that's all debug information that you can use to test out what's going on in the world. Just at the moment, actually, the debug information is a frame behind the actual visual, the graphical representation. So a lot of people have been asking for this in the forum. Stacking is a big issue with the friction model that's in Unity physics. It means that we don't have that cache to deal with the velocities over frames, so stacking is a bit of an issue. The forum did ask for 3 bodies stacked on top of each other, but with Havok physics, you can actually stack quite a significant amount more. And as of this morning, we have our first release of a game, if you can call it that, using Havok physics. So it was only released yesterday, and someone's already put something up on Twitter. So they are really pushing the stacking within Havok physics. So restitution, bounciness, is another issue. Each one of these scenarios that I'm showing here is kind of a worst case scenario. It's just to really illustrate the differences between these two backends. But they are representative of all of the sort of use cases that come up in game development. So restitution or bounciness, this example demo that I'm going to show here is a worst case scenario in that it's 12,000 convex hulls all piled up on top of a static mesh. We'll use that for performance differences later as well, but there's two things going on. This character is spawning a large number of these convex hulls every frame, so there's a little bit of interpenetration going on, and there's also a high restitution on these values, or on these convex hulls on the material properties. Within Unity physics, both of the interpenetration energy that's gained and the restitution model, which is not quite as, I'm always worried about the word here, but maybe refined is reasonable enough, means that you get this effect. Now, you might want that effect, that's fine, but at least with Havok, you don't have to have it, or you can have it if you want. So they are still bouncy, but the penetration recovery is not causing a large amount of energy to come out. So just the two of them together. Now, I will point out there was a large amount of time spent. We don't want to knock one engine and promote another engine. There's different use cases in here. You may want that. So it's up to you to choose which one you want to prefer. So I already mentioned that we're a speculative continuous collision detection. We're not going to get performance spikes in the way previous iterations of Havok and other engines had, but we do have other issues that come up from that particular approach we use. And that's with speculative contacts. So in this particular image here, we're actually picking up, these are the boxes sliding down a tessellated mesh, and we're picking up edges off an upcoming triangle. And you can see that the normal for those edges are actually going towards the box as the box slides down. So sometimes it's called a ghost collision. It's a speculative contact where the contact normal of the edge that you're seeing, and this is a mesh with two triangles, and we're approaching from the left, and we end up hitting the edge of the second triangle, which acts like a contact normal and deflects the ball up into the air. Now, with meshes, we can sort of get away with that. So in this is one of the examples that's in the the Unity sample set. Here is a sort of jittering type collision response you're getting from those speculative contacts. But one approach you could do is to use the callbacks that we talked about earlier, take the contact information that you are provided, and just mess with the normal. Turn it to be the face normal rather than the edge normal of the upcoming triangle. Or in the particular demo, we just go, we know that this is a flat plane, really, even though it's tessellated for whatever reason. And we can just set the contact normals to be all the same. Now, that's not necessarily going to be appropriate for the generic use cases. It might be absolutely perfectly fine for yourselves. It does highlight the fact that we want people to be able to dig into the core source code and enhance it for their particular game use case. So here is the particular demo. You can see that the speculative contacts, while we're picking them up, we're also rotating and scaling those contacts so they don't actually have an effect on the box as it slides along. And as I say, it might be good enough for a specific use case that you're looking for. But it's much more difficult whenever it comes to dealing with coming up on the edge of a body as you move. So again, with a triangle mesh, you can get some of that information from the mesh. If you're coming up on a body, again, you're picking up the contact point because you've expanded the ABB of the dynamic body. You pick up a speculative contact point, and again, you get the deflection, which shouldn't really be there. So when we come to Unity physics, this particular is just a worst-case scenario again, and you probably wouldn't be firing tiny balls through the world. You'd probably be using raycasts, but it does highlight the issues. This is a set of corridors, a very thin corridor in the middle, and sort of slightly wider ones to either side. We can see from the fact that the ABBs get smaller when the bodies come out the other side of the corridors, that the velocity has been trimmed because of the contacts that are picked up. And it might be difficult to see, but you can see that the balls that are firing along the edges of the larger tunnels are actually being deflected in towards the center because they're picking up those speculative hits. And again, the visual debug functionality that's inside Unity physics highlights this sort of information as well, which is quite useful. Might be difficult to see, but you can actually sort of see the actual contact points and see where they're coming up and step it over time. So with Havok, this is one of those things that we don't necessarily want to enable out of the box. There's a small performance hit in order to deal with these speculative contacts. So we don't turn it on by default for Havok. There is a Havok configuration authoring component that you can add on to an entity that's dealing with your core physics setup. And one of those options is that you can set up a particular custom tag, sort of the body tags that Adam was talking about in the last session. And you could set one of those up to say, I want to enable, we're calling it welding, that's subject to change because welding works on a mesh level, but it doesn't work between bodies. But if you could set up a particular tag to say, anything with this tag should deal with those speculative contacts, those ghost collisions in the world. And so when you have that turned on and opted into in Havok, you can see that the bodies fly through the corridors, they don't get their velocity trimmed, and we're dealing with those ghost collisions. It's also worth highlighting that you might not hit this scenario. You're really only going to see these things whenever you're dealing with larger time steps, with fast-moving objects, especially over that sort of use case, which is a flat tessellated terrain. Now that use case, those were sort of fake, exaggerated use cases. A real use case might be a vehicle. So this is a vehicle with low suspension. That isn't quite flat, so there is a little bit of jump from the suspension. But, you know, again, if you want the rodeo type effect, you can have it, but it's not something you have to take with the Havok opt-in option. Okay. So the last piece is on performance. And part of that is deactivation. So this is on by default because I can't actually think of a use case why you wouldn't want things that aren't doing anything to fall asleep. But again, it is toggleable if you do need to force everything active every single frame. At a high level, you know, you can see that the blue boxes, any object with a blue box around it is active at the minute. It's going through its collision detection and response. And then after a few frames, it'll be deactivated, and certain clusters of objects will sort of just turn off and not sort of deal with any simulation each frame. Reactivation then happens whenever a body moves through the world and overlaps with that group of deactivated objects, and it just turns on that specific group of deactivated objects. Now, this looks trivial, but it's actually one of the hardest things. That is lots of tendrils in the Havok SDK. There's a lot of scenarios where deactivation comes into play. If you're adding and removing the bottom object from a stack, you need to reactivate. If you're firing a raycast and you want to apply a force, you need to make sure you're reactivating on that force apply. And of course, you need to reactivate if you're going to actually bounce off things. So in certain cases, it's possible to do. You might, some Havok Physics users are maybe just, rather than deactivating, making a set of bodies that aren't really moving very much. You might make them static rather than dynamic. And that's that's an interesting use case, because it just means they have to remove the physics velocity component from their entity, and that makes it static. So it's actually quite easy to do that. But then they have to do the spaghetti code in order to make sure that they reactivate things appropriately. And if you know the use case in your game very well, that might not be a problem. Work away. But if you want to sort of opt into Havok Physics, this is one of the things that are done for you. So finally, I want to just touch on the CPU use case. Again, we'll go back to this previous demo, 12,000 convex hulls all piled up on top of each other. Pretty extreme example, of course, but what we're seeing is roughly about a 2x performance increase on these sort of scenes between Unity and Havok Physics. Yeah, that's scaled. I don't know how to present it in a slightly better way. But you actually can end up with a much better performance increase whenever you're dealing with a larger environment with bodies that are scattered around the scene rather than all piled up on top of each other. And then deactivation kicks in, and you're actually only simulating, one or two of those bodies at any particular point in time where your character is sitting. So finally, I want to just touch on something that's in the Havok SDK, in the Havok Physics plugin, and that's an option for a much more detailed investigation tool. So this was an early version of the Planet Gravity demo where something went wrong. I'll ask, can anybody guess what the problem is here? No. Sorry? It is, but the main problem is that the planet accidentally had a box shape instead of a sphere. And if you're only looking at the graphics, then you're going to start looking at center of mass and where your forces are being applied and having to deal with all of those what-if scenarios. But because you've got the physics debug display option, which we do need to optimize, we do need to make it faster, but you just turn it on and you can immediately then see what the problem is in a visual way. Within the Havok plugin, there's something called the Havok Visual Debugger, and it's just basically a much more detailed version of that. If you're got the plugin installed, you will see an extra menu under the analysis, the window analysis menu, called the Havok Visual Debugger. And it can give you a lot more detail and deal with much bigger simulation scenarios than the built-in Unity physics debug information. It is a Windows PC client, but it does connect remotely to wherever the game is running on, whatever platform the game is running on. It's got a scrubbable timeline, so you can pause the game and scrub backwards and forwards and try and find that exact point that maybe a collision response isn't acting quite nicely. It's got a lot of data visualizations, like just seeing the colliders, but you're also seeing the contact points. You can see in this particular example, we've got the motion trails, which is brilliant. We're actually probably wanting to put it into Unity physics, but it shows you the motion over time. You can start to see some of the pieces there deactivating and going green, although obviously at the moment a lot of them are active and representing in blue. You've also got the performance metrics, which dig down and show you information quite like the profiler in Unity itself. And you can actually, inside the visual debugger, pick up bodies, move them around, and they will update on your game as well or in the editor. So there is an actual two-way interaction there as well. One of the particular visualizers I want to highlight is the heat map. We're finding a lot of use cases where both the designers as well as the programmers are finding this useful. This is basically highlighting graphically where the CPU load for the simulation is in space. And it's quite nice to see the sort of heat map expand as you start piling on bodies on top of each other in that previous 12,000 convex hull demo. So sort of a little pause and show some real game use cases where they have sent in their visual debugger information for us to look at and try and help them debug a particular problem in the physics world. So there's a little bit of customization the guys have done here. You can see in the bottom corner, they're using a pencil type shape for the character controller, which is interesting. They're actually drawing the camera view frustum as well in those sort of cyan colored rays. Obviously there was a large explosion there, and they were drawing the forces that they were applying on the objects. And these are some of the vehicles, obviously, well, maybe not, maybe it's not obvious. But can anyone name the game? Haha, well done. I wish I had like a t-shirt gun I could send out swag. So that's the same sort of scenario, only with the large amounts of particle effects added into the scene. The explosions do make a bit of a difference. But I could watch that all day. So here's another example, again, when we're talking about the vehicle use case. You can see that lots of debris pieces are flying out, but the road itself has the odd bump, but it's mostly smooth. We're seeing the broad phase in the world here. We're also seeing constraints being represented on some of the bodies previously. And as this goes through, you start seeing these red boxes are trigger volumes, so the car actually drives through them, but we can visually see where the trigger boxes are. Anybody know this game? It's a bit hard to guess, but... Sorry? Uncharted? I do have a VDB movie of that, but I'm not allowed to show it. No, this is MotorStorm Apocalypse. So you can just see that, again, the graphical, sometimes there's a disconnect between the graphics and the physics. Here, the road has got a lot of debris pieces on it, but none of those are being simulated, because that would make a horrible driving experience. But hopefully, you could see how the actual gameplay mechanics are all represented in the physics world. Okay, I've got one final one, a different use case again. This is interesting because the red boxes are supposed to be axis aligned, but obviously they're not on the canonical X, Y, Z axes. So in this particular case, we're standing on a planet about where Spain would be. Can anybody guess the game? Well done. So I believe this is the actual planet that they were going down onto, because you can see those sort of spiked curve structures whenever the spaceship lands. So it's very interesting that those game developers are sending us the visual information, and we can help debug this sort of scenarios just from that physics information itself. And also, and being able to visualize that immediately lets you see specific problems, like the planet being a box rather than a sphere. Okay, so just want to summarize the sort of core differences, and hopefully this isn't just marketing speak, it's just to give you information. So we are using the same data. We are getting better performance. We are getting better behavior, or behavior that you can opt into if you want. And all of this technology and all of the core underlying Havok simulation is definitely battle hardened, and some of the games that are using it we saw directly there. And this is available now in the package manager. Please go grab it, and please give us feedback on the forum and on what your experiences are. So there's a lot of stuff in the Havok Physics SDK that isn't maybe necessarily represented in the component data interfaces at the moment. And I just want to show some of the things that are in Havok Physics that we could enhance the Havok Physics offering more with these features. One of them is convex decomposition. The SDK at the minute is providing simplification of convex objects into convex hulls. It's dealing with data that's very noisy and still producing convex hulls that are quite good. It's producing unstable cows and horses. And the use case is a little bit less common, but it can break down sort of static environment into sort of a series of convex hulls based on the level of detail you want. Another option is optional penetration recovery. This is useful if the designers are wanting to put a specific stack of dynamic objects in the scene, but they don't necessarily want to line them up perfectly, so you don't get that sort of initial, hopefully we've all seen that, where a stack of boxes just sort of have to settle and move a little bit. But we can turn that off, and we can ignore certain contact points that stop objects going further into penetrative state, but allows them to come apart. Again, useful for that sort of explosion use case, or just means that the designers can be a little bit more lenient when they're placing dynamic objects around the scene. Havok Physics has also got a much more accurate aerodynamic model, if that's needed, and a buoyancy system there as well, although the boat attack demo that you can see on the stage with the universal renderer, they have been playing with doing the buoyancy in dots already, which is quite interesting. And there's also a pretty big piece in the Havok Physics SDK. Haven't worked a good name out for it, but lower fidelity rigid bodies is a reasonable term. This might mean that we could have something, we've had physics collider as a component, we've got physics mass, we've got physics velocity. We could have a physics quality component. Now, that particular component might not do anything with the Unity physics backend, but it could actually use the lower fidelity rigid bodies that are available in Havok Physics. And you're getting, on top of Havok Physics, you're getting another 8 times CPU performance increase. And here's some examples. So that worst case scenario of piling 12,000 bodies on the surface, it now becomes possible with the sort of performance you can get from these lower fidelity rigid bodies. And it's not just, well, actually, this particular scene at the bottom with we're shooting up bodies, we're showing the difference between what would happen if you used a full-fat rigid body. Full-fat, is that the right term? Or the low-fidelity version, and you can see the sort of performance graph on the bottom and see what the differences are there. They're not going to be as accurate. They're not going to be perfectly stackable. There are going to be trade-offs, but they are going to be incredibly cheap. And you could have a 6-DOF version where you're having rolling boxes, and you can have an even simpler one that's just a 3-DOF particle, as the one in the top right. Here, we're actually colliding with a full mesh geometry for every single particle there, but it's a 3-DOF version, so it's a lot more performant. So that is me. I'll hang around for questions after this. We are on the Expo Partners area in the Microsoft GameStack booth. And I am going to be at the expert bar tomorrow as well if there's any more detailed questions, but I'm happy to take questions now as well if anybody has any. I think there's microphones up there if anybody does want to ask.
Yeah. What about soft bodies?
We're entirely focused on rigid body simulation. So the question was, what about soft bodies?
Yeah.
We are entirely focused on rigid bodies within these packages at the moment. That said, things like the soft contact modifier would let you introduce a soft body type response in the collision, but it really is something that you would have to put into your own game.
Okay, and about the springs and all those connectors between rigid bodies?
Constraints?
Yeah.
Okay,
like
so the runtime, as Adam said in his talk, there is the runtime Jacobians for constraints. We have ball and socket, we have prismatic, we have a sort of a rope type constraint. We have a ragdoll constraint specifically for hips. The piece that's missing, that's all there. That's all there in the runtime at the minute. The piece that's missing is really the authoring and letting you set that sort of stuff up. That is there in the samples. There are some example authoring pipelines for some of those constraints, but that is a focus that Adam and the Unity team are going to be looking at in the next couple of months. Did that answer your question? Sorry, I can't see where you are.
Yeah. Yes, thank you.
Okay, brilliant. Anything else?
Is this
Hello?
Oh,
Oh, sorry.
sorry. Yeah, I wanted to ask how well Havok Physics integrates with dots? Are there any disadvantages using Havok Physics instead of using physics?
At the moment, physics is entirely focused on the game object side of things. And Unity and Havok Physics is entirely focused on dots. Some of the advantages might be, one that came up on the boat attack sample was if you're trying to apply a buoyancy model to a rigid body. In mono behavior, you're applying that function on every object in their own specific mono behavior. In the dots world, applying those sort of forces is in one job, and you can stream through all of the data that has, say, a buoyancy component on it. So there's actually some significant performance benefits for the dots approach whenever you're coming to a lot of physics use cases. Does that answer your question?
Yes, thank you.
Okay, thank you. Anything else?
So, do you have the demos publicly available?
The demos are, I can bring the demos up here. These demos are available on the GitHub repo with the standard entity component system samples. So there's a Unity physics sample subfolder in that GitHub repo. Sorry, I should have had a slide with that particular talk, or with that particular project linked to it. But all of the samples are there showing individual setup scenarios where we've got things like, let me see, where we're messing with the inertia tensor on the bodies. And so whenever we play this, some values have got an inertia tensor where they're not allowed to rotate. Some have got sort of like a weeble where their weight's at the bottom. The samples are really there for you to play with individual pieces of the physics system and get an understanding of what each component does, whether you just want to mess about with mass, whether you want to mess about with constraints, or whether you want to mess about with the inertia tensor, so you see that the boxes aren't falling over, or they're falling over slowly because we're messing about with the inertia tensor. Someone did ask about constraints, so this is an example that goes through setting up each of these, and this is kind of like a joint parade where we can see all of the different constraints. There's a little bit of, this is a sort of an issue that the guys are trying to improve. The pause here as the game starts is burst compiling all of the scripts. They are looking at caching that in I think, 2020. I can't exactly remember which version of the editor. But here we're seeing the different constraints that are possible. So let me see if I can zoom in here. We've got a prismatic constraint here, linking the dynamic and the static body. We've got a hinge. This is a limited hinge. This is just a point-to-point. Oh, that's the ragdoll demo, or the ragdoll constraint, sorry. So we can go in here and see the sort of visualizations of the limitations that that particular body is allowed to move within the constraint bounds. So all of the demos are in there. You'll have to excuse the programmer art. They really are there just to show the features of physics. And I'm not going to say that I'm an artist in any way. Did that answer the question? Oh, yeah, time up. You. Okay, thank you very much, folks. And I'll be around if you want anything else.